Now I'd like to introduce the notion of spectral density. There is a very important fact in the probability theory, so-called Bochner-Hintschen theorem, which states that the function phi is a characteristic function of some random variable xi if and only if the following three conditions are fulfilled. First of all, the function phi is continuous. Secondly, it is positive semi-definite. Since phi is a function from R to the set of complex numbers, positive semi-definite here means that the sum zeta j, zeta k complex conjugate multiplied by phi is a point uj minus uk should be non-negative for any set of complex numbers z1 and so on zn, and for any real u1 and so on un. Here the sum jk from 1 to n. And the third property is that the function phi at 0 should be equal to 1. This is not a difficult exercise to show that if function is characteristic, then all of these properties are fulfilled. All of them follows by simple calculations. More sophisticated part of this theorem is the inverse statement. So it turns out that for any phi which satisfies these assumptions, there exists some random variable such that phi of u is equal to the mathematical expectation exponent in the power I u xi. Bochner-Hintschen theorem is a general mathematical concept, and it appears in some forms in other fields of mathematics, like functional analysis, in real analysis, and other parts in calculus. And actually there are many alternative formulations of this statement. For instance, if we omit the third property, so we assume only the first and the second, then an analog of Bochner-Hintschen theorem still holds. Namely, there exists some measure mu such that phi of u is equal to the integral exponent I u x multiplied by mu dx. So mu can be not a probabilistic measure. Definitely it is not a probabilistic measure since phi of 0 is not equal to 1, but there is still some measure. Another alternative formulation is when we assume 1, 2, and also assume that integral absolute value of phi of u du is finite, then in this case the measure mu has a density in the sense that the function phi of u is equal to the integral exponent I u x s of x dx. So there are various alternative formulations, and in our case it will be more important the last one. Well, which function we can take as a function phi? So assume now that we have a process xt which is weakly stationary. Therefore, there exists a function gamma, outer covariance function, such that covariance function of the process xt at time points t and s is equal to gamma as a time point t minus s. If this function gamma is such that it is continuous and also integral gamma of u du is finite. Then we can apply the theorem of Bochner-Hintschen in this form, because any function gamma is positive semi-definite. This is a simple exercise to show this, and actually this fact follows from the properties of the covariance function. Therefore, in this case, there exists some function g of x such that gamma of u is equal to the integral exponent in the power I u x g of x dx. This basically means that gamma of u is the Fourier transform of the function g at the point u. On the other side, any Fourier transform has inverse operation. So we can say that the function g of x is equal to 1 divided by 2 pi integral exponent in the power minus I u x gamma of u du. And this function g is actually exactly the spectral density of a weakly stationary process xt. This is a definition, and there is a discrete analog of this function. So you know that there is an analog of these statements. They are based on the so-called Helmholtz theorem. And if we proceed exactly in the same way for discrete time processes, we finally get that the function g is equal to 1 divided by 2 pi sum of all h from minus infinity to plus infinity exponent in the power minus I u I h x gamma of h. And in the discrete time, the spectral density is defined exactly via this formula. In the next subsection, I will provide some examples of the spectral density, and also I would like to discuss the main properties of this object.